first design, fairly schematically here, you can see flanges, which are these plates, and you can see the ribs, which are curved here. And then you have this outer ring on this side and an inner ring that drives the impeller. All the parts are made with this layout. Now, in the future, we knew that we would start with this layout and progressively we can improve the fiber orientation. We ran some simulations and we compared Inconel to a quasi-isotropic laminate impeller as shown on the previous slide. And what we simulated was what kind of stresses do we see in the part when it spins at 40,000 RPM. And what we could see that at 40,000 RPM, the maximum stresses in the bulk, so I want to specify, this was, there was some hypothesis, so we're not, we're only using centrifugal loads. We were clearly discussing this, of course, with producers of centrifugal compressors, OEMs, that told us that the aerodynamic loads were practically zero compared to the centrifugal loads, so they could be neglected. The mesh was not fully optimized and the stress concentration was ignored at this stage. So it's really the bulk stress here that came out at 2,400 megapascal, which meant that in reality, you could not spin any faster than 28,000 RPM. With the composite impeller, even at 40,000 RPM, we were still only at 550 megapascal bulk stress, and therefore the speed could actually be slightly increased before we reached the 750 megapascal elastic limit or strength. And what you can see between these two numbers is that there is a factor square root of 3, which is exactly what we expected. I was showing you previously a difference by factor 3, but here, compared to the speed, we have a quadratic function. Therefore, the difference is square root of 3. Here's the test. I'm going to run the test quickly so you can see, I don't know how scattered it is on your screen, but you can see that the back plate completely blew away at 31,000 RPM. So much lower than we expected. In fact, that equates to a tip speed of 500 meters per second. Now, 500 meters per second is higher than what you would see with metals. If this was made from metal, it would fail around 440 megapascal, 440 meters per second. But this is still not enough to compress hydrogen. I'm going to show you again, and I'm going to pause just to show you the initiation. So around here, you can see a first piece that comes out. And in fact, the stress, as you know, is the highest on the ID. And even if we had the hoop ring, it didn't really reinforce it enough here. And we start to see a failure. You can see here like a square. This hole almost became square here. This is really the ID where the plate started to break. And then progressively, I think you can even see like a screw hole. This was the bolt here. It was here originally. And if I go back, you can see how it falls out. So this entire back plate was destroyed. So from this learning, we made a lot of changes. So first of all, we knew that having the drive mechanism as it was and to run to cut a hole into the plate is really quite detrimental. Of course, we knew that before, but we were hoping that the hoop ring would take on these internal stresses, which didn't work as we expected. So we started thinking around a method of driving the impeller without holes, another mechanism. And when we tested it, it was a big disappointment. In fact, we saw that these ribs or blades here were ejected at 534 meters per second. So of course it's better than the previous test, but it was still quite far from the target of 600 meters per second. So we came to the third design iteration. And in this case, we really looked at a number of materials that we could use. And they're all carbon peak steel, but there's a number of suppliers and a number of fibers out there and even polymer suppliers are different, and everything was tested for interlaminar tensile strengths because this we knew was one of the weak points of the previous test. And we also looked at optimizing the molding process to avoid the fiber misalignments. And finally, a design change where we remove the conical section at the top. It's not necessary for composites to make a thicker section in the middle because the plate is absolutely not the critical failure point of our impeller. The second thing we changed was the molding. So we optimized our molding process, and you can see we managed to get completely rid of the folds and the fiber misalignment. We even tested these. This was a coupon test, so it was a mold that was not making a full impeller, just 2 ribs. We tested them either by pulling them apart or by pulling on them in the axial direction, and had very, very consistent high results, which were also a great support for our FEA model to feed our model and to be able then in the future to predict any geometry that we would want to make for a customer. And then we put another camera into the machine and test and spun the impeller until failure. And if you look at how fast things happen, so this is at the time, let's call it 0 millisecond, and you can see the first rib come out. So we still had ribs that were expelled. In fact, at 0.1 millisecond, all the ribs are coming out, and in less than 1 millisecond, all the ribs are gone. And we already saw a first crack in the plate itself. A little bit later, a very short time after, in 1.2 milliseconds, the ring has cracked and ended up cracking in 5 areas, so that 5 pieces within less than 2 milliseconds, or about by the time 2 milliseconds are in, all these pieces are out and gone, so the whole plate disappeared. So during this third impeller testing campaign, we reached our target, because the failure that you see here, or in fact the initiation, which I was showing here, which is practically the same, happened at 688 milliseconds. Meter per second tip speed, excuse me. This is 47,800 RPM with a diameter of 275 millimeter. What I was showing before is the 20,000 RPM. So at 20,000 RPM, the maximum displacement that we saw with the digital image correlation was 0.22%. So it is very easy to calculate what deformation we had just before failure, because it's a linear function. It's a quadratic function with speed, and between 20,000 and 47,800 with a quadratic function, this gives us an estimation, but which we can really be quite sure of, is a deformation of 1.26%.